Okay, welcome back everyone. Moving on to chapter 6, this final chapter of the entire text and semester. It's only going to have 2 sections in it as well. Thinking about related applications. I've been teasing this for a little while. We studied, there are many reasons to study integration techniques, but we studied some particular integration techniques such as partial fractions, trig sub, and other trig integrals for the purpose of doing calculus with parametric and polar curves. So not uncommon that you would expect something like the parametric version of a polar curve naturally has this cosine inside of it and a sine inside of it. So if you want to do any sort of calculus with, these sorts of curves, this xt and y of t, that maybe come out of a polar curve in the first place, you're going to be doing a lot of calculus with trigonometric functions. So that's really why we had to study a lot of those. And you'll recall, like, partial fractions just kind of was the way you had to integrate some of these if they were rational functions of trig functions. Anyway, today we're going to focus on arc lengths and areas. Now, arc lengths is probably something you haven't even seen for regular functions, f of x or g of y functions. We're going to come up with an arc length formula first, and then we'll get over to areas in a bit. Let's think about what an arc length formula might look like. It works out best for parametric curves, just because these are kind of the most general version of curves we can construct in the plane. And so if you have a parametric curve, which is x as a function of t and y as a function of t, you can calculate that the total arc length over this interval t min to t max is going to be the integral, definite integral, starting at t min, ending at t max. It gets a little tricky. You have a square root of the derivative of x squared plus the derivative of y squared. And I want you to think, we're going to see where this comes from a little more explicitly, but you should really think that this is the distance formula, or equivalently the hypotenuse of a triangle, where you're putting x prime in the horizontal direction of the triangle and y prime in the vertical direction of the triangle. If you use the Pythagorean theorem, a squared plus b squared equals c squared, equivalently you see that c is the square root of a squared plus b squared, and that square root of x prime squared plus y prime squared is really what's going on in your arc length formula. Why does this make sense for arc length? That hypotenuse is really describing the total length, the total distance between a starting point and an ending point if you move some amount in the x direction, movement corresponding to velocity corresponding to a derivative, and some movement in the y direction. Right, so depending on how you move in both the x and the y direction, kind of the total movement amount can be computed as this hypotenuse. And so you're just going to add up, right? An integral is a sum starting from one point to another of the total movement, more or less, total displacement. There's your arc length. So that's how we can think about that formula. I have the proof here a little bit better, but I've just kind of described that right triangle here where you have a movement in the x direction, or velocity in the x direction, movement in the y direction, velocity in the y direction. So then your total velocity is really the square root of x prime squared plus y prime squared. And then you just sum up infinitely many of those total movements. Now there's a direct corollary to the formula I gave in the parametric setting, where we can actually extract the version of really just regular, this is a regular function of x, so f of x version, rather than a parametric curve. So if I just have f as a function of x, maybe I have something like f of x equals x squared, so that's just this parabola. Could I calculate the arc length of some interval on the parabola? Yeah, it's not too bad. It comes straight out of the parametric curves, because you can always represent these functions as parametric curves if you want to. That's going to look like the square root of 1 plus the derivative of f squared. And that 1 is really playing the role of 1 squared. Similarly, if you're working with a function of y instead, you could have something like this is x equals y squared. And maybe I want that arc length. Do the same sort of thing. When you start at some minimum value of y, you integrate up to a maximum value of y, and you have the square root of 1 plus g prime of y squared. And in the polar version looks a little bit different, but you can imagine, remember polar curves, it's r of theta is some expression of theta. And one of these common curves may be like the Archimedean spiral, something like that maybe. You could calculate the arc length of the Archimedean spiral, maybe over that range, some minimum to maximum theta value. Now this one looks a little bit different. It's the square root of r squared, but you also pick up the first derivative of r squared. Very interesting that you get both the radius and its derivative inside of the square root. They all are, at the end of the day, calculating a version of the hypotenuse in the Pythagorean theorem. That's why you always see a square root of two things added together squared. I've got proofs of all of these. I think the only interesting one is the polar case. So let's recall that in the polar setting, you can represent a polar curve that would be regularly be r theta comma theta in polar coordinates. You can represent it in Cartesian coordinates or equivalently parametric curves by taking the x value of the parametric curve to be r cosine and the y value of the parametric curve to be r sine. And then you're basically letting t and theta be the same variable. And then all I've done here is, this is really ugly. This is just my parametric arc length that we started with, t min to t max root x prime of t squared plus y prime of t squared, and then dt, and I've replaced that x prime with me actually using the product rule on rt cosine t, and you get this whole big term squared, and then similarly with y prime, you use the product rule on rt sine t, you get this whole thing squared. Looks pretty ugly the way it is. If you go through the work of foiling the first parentheses squared, you're going to get this entire term. If you FOIL the second parentheses squared, you get this entire term, and you'll notice what happened is that the inside terms crossed out, because you had a minus here and you had a plus there. And then what you're actually left with, if I group terms correctly, is a cosine squared plus sine squared with the r prime. And then you have a cosine squared plus sine squared with r. And of course, cosine plus sine, the Pythagorean identity, not the theorem, but the identity, makes them 1. So those are both equal to 1, and you just get r prime squared plus r squared. So that's a very nice little algebra to show that you can compute the arc length of a polar curve as well. We're going to provide one example of a parametric arc length and one example of a polar arc length, because the other ones are just as easy. You can send everything into the parametric version. We did cover how to send every curve into a parametric curve, so that one really is the strongest of all the arc lengths. Let's start with the logarithmic spiral. If you don't remember what the logarithmic spiral looks like, it kind of looks like this. It's exponentially decaying towards the origin. And so you can see that with the e to the minus t here. So it's exponential decay, and then cosine and sine are kind of telling you to, behave like a circle whose radius exponentially decays as you walk around. Okay, so we're exponentially decaying towards that origin. We can actually compute the arc length all the way out to infinity here. That feels kind of strange, but because it's that exponential decay, your curve is starting out here and it's getting close to the origin. It just ends up wrapping around the origin just infinitely many times, but in a very, very small manner. And so we'll be able to go all the way out to infinity for this arc length. Kind of surprising, but we'll see that it works. What have I done here? Let's recall what actually happened here. This entire piece is x prime of t. I just went ahead and used the product rule on x. This entire term is y prime of t. I use the product rule on y. And kind of like before, I'm going to FOIL each of these out with the squares. Looks like I was missing a square there. I'm going to FOIL each of these out with the square. And what that's going to give me, well, it's going to give me the first term squared. That's what I've got there. It's going to give me the last term squared. That's that there. It's going to give me the cross terms, which is this times that. It's going to give me 2 of those cross terms. So that's the first one squared. The second one squared will give me the first term squared. There it is. And the second term squared. There it is, as well as 2 copies of the cross terms. There they are. Because the cross terms here is minus times plus, I'm going to have a minus. Here I have minus times minus, so I have a plus. And because of that, those cross terms in this case are canceling. And in fact, I'm still going to have a version of the Pythagorean identity, meaning, let's notice our coefficients, e to the minus 2, e to the minus 2, e to the minus 2, and e to the minus 2. I can factor all those out. I'm going to end up with 1 copy of cosine plus sine and a second copy of cosine plus sine. So that's why I have 2 e to the minus 2t total terms of a cosine squared plus sine squared. Because of the Pythagorean identity, that's equal to 1. Turns out that I'm just the square root of 2e to the negative 2t. My square root's the same as a power 1/2. Power 1/2 can multiply in the current exponent. Negative 2 times 1/2 is just negative 1t, as well as a root 2 that I'm pulling out front. Antiderivative of e to the negative t. That negative's playing a little bit of a u sub role here, so I'll get a negative out front. Then I'm going to evaluate my bounds of 0 and infinity. So this is an improper integral. If I plug in infinity, of course, or take the limit at infinity, that's exponential decay. I'm going to decay to 0. If I plug in 0, e to the negative 0 is just going to be 1. So I have minus negative 1, also known as positive 1. Turns out that this total arc length is square root 2. So even though it's a quote-unquote infinitely long curve, because it gets so close to the origin, that curvature gets infinitely quick near the origin, I only need a finite amount of arc length. Somewhat surprising, but also very cool. Now, it turns out that if we just switch from a logarithmic spiral to an Archimedean spiral, our integration gets really hard. We're going to see all of our lovely integration techniques show up in our next example, which is just to calculate the arc length of an Archimedean spiral instead. So the Archimedean spiral is going to be defined by the parametric functions t cosine t and t sine t. And in this case, I'm just going to let t range from 0 to 4 pi. That's saying I want 2, that's 1 full revolution 2 full revolutions of this spiral is what I'm going to calculate. You could calculate that as high as you wanted to. Now, how are we going to compute the arc length? It's the same as before. We just calculate x prime of t, and we're going to square it. We calculate y prime of t, and we square that as well. And when I FOIL the first term, I'm going to get the first piece squared. I'm going to get the last piece, t sine t squared, and I'm going to get twice times the cross terms. Same with the second case. I'll get the first term squared, the second term squared, and 2 copies of the cross terms. And as before, I have a negative cross terms and a positive cross term, so those cross terms perfectly cancel out. This won't always be the case. We're just getting lucky with everything we've developed here. So the cross terms have canceled. I'm again looking for some Pythagorean identities. It looks like I have a cosine squared plus sine squared, so let's group those together. And a t squared against cosine squared, a t squared against sine squared. Let's group those terms together. They're both going to be 1 individually. I'm going to end up with the integral from 0 to 4 pi 1 plus t squared. Now, how do we integrate square roots of quadratic functions? Please tell me you remember how to integrate square roots of quadratic functions. There's exactly one integration technique that's built for these. That integration technique is trigonometric substitution. So the first thing you want to recognize is, big question, do I have a square root of a quadratic? If the answer is yes, trig sub's the way to go. If we're going to do a trigonometric substitution, it's already in completed square form. Recall the only way to tell if you're in completed square is if you have any single power terms of t. You don't want those for completed square terms. So if this were like 1 plus t squared, I would not have a completed square. But because it's just 1 plus t squared, this is already a completed square. It's a completed square of something plus another thing. We're going to make the trig sub with tangent. So we'll do tangent of theta is equal to t in this case. If I make the trig sub that t is equal to tangent of theta, well, you can take the derivative of t pretty easily. It's going to be secant squared theta d theta. And so I'm going to swap out dt for secant squared d theta. There it is. I've swapped out dt. I'm going to swap out t for tangent. So t squared will become tangent squared. And let's recall the Pythagorean identity. We're using that all day, by the way. Pythagorean identity. Well, you can either say it's cosine squared plus sine squared equals 1, but if I go ahead and divide everything by cosine squared, I get 1 plus tangent squared equals, well, 1 over cosine squared. 1 over cosine is the same as secant. So you find out 1 plus tangent squared is secant squared. Swap in a secant squared. You now have a square root of a square. You can call this the integral of secant cubed. Now at this point, our life actually gets quite tricky. I haven't gone through all of the work for this. If you go back one chapter, we do have the tools to compute the integral of secant squared. You have to follow this process where you start with Euler's identity, cosine being, 1 divided by secant, so secant is 1 divided by e to the I theta plus e to the minus I theta all over 2. So you're going to cube that. Then you're going to expand that denominator in terms of e to the I theta. Then you're going to go ahead and make a substitution. U is e to the I theta, so that du is I e to the I theta d theta, or equivalently I u d theta, or equivalently that d theta is minus I 1 over u du. So you make those substitutions. That will give you a rational function in the variable u. And you can use a partial fraction decomposition to decompose the rational function of the variable u as a collection of simple rational functions. And once you have a collection of simple rational functions, you can integrate the partial fraction decomposition in the variable u. Then you can make the reverse substitution that u is e to the I theta, so put a bunch of e to the I thetas in there. Then you'll be able to simplify the expression in terms of Euler's identity. You're looking for, e to the I theta plus e to the minus I theta over 2 for cosine, and you're looking for e to the I theta minus e to the minus I theta divided by 2i for sine. Some version of all those will let you simplify. We've saved you the headache in this case. You end up getting that the integral of secant cubed is 1/2 secant tangent plus 1/2 log secant plus tangent. Pretty ugly stuff. I wouldn't advise going through it. You can look this up online. There's lots of other ways of integrating this as well, using some trig identities. So just something people have discovered for powers of secant. We have the ability to do it. I think it's probably not worth it to go through all of those steps to really see how to compute the arc length here. That's going to be the integral of secant cubed. So now that we know it, let's recall this was our original integral, except we sent it into this integral using trig sub. And then we went through that process, even though I didn't make it clear, to find the antiderivative of that integral, and then we're going to make the reverse substitution from trig sub, which was that theta was the inverse of tangent in the variable t. So that theta, that theta, that theta, and that theta, I'm plugging in inverse tangent of t. Then when I plug in inverse tangent, well, I can cancel tangent of tangent inverse, cancel tangent of tangent inverse. Those are pretty easy. Secant of inverse tangent, I did go over in all the way back in the trig subsection. So if you want to go back to the trig subsection, you can see that the simplification of secant tangent inverse is 1 plus t squared. And so I've just replaced them with 1 plus t squared in both of their cases. So that's going to be the antiderivative of the square root of 1 plus t squared. Doesn't look great, but you can certainly calculate it. And now that we've done that, right, this antiderivative computes the arc length once we put some bounds on it and give ourselves a definite integral. So we're going to put some bounds on this antiderivative and compute the definite integral, bounds of 0 and 4 pi. We're going to end up with kind of this extra large collection of junk, where if I plug it into my calculator, I get 80.82. So it turns out that that arc length, this first arc length I looked at, up here is about 80.82. That's the length of string I would need if I pulled this string out flat. That makes sense. I mean, it looks like we're going all the way from 0 to maybe like 13 out there. And yeah, there's probably quite a few copies of that length built into the curve, right? Maybe 1, 2, 3, 4, 5, 6, 6.5 times 13. Yeah, it sends you to 80, right? 80 or so. There you go, 80.82. Pretty good. All right, so we're going to move on to away from arc lengths. I mean, they're just special integrals that you set up depending on your parametric curves. We're going to do the same sort of idea, but we're doing it for planar regions. So these are going to be regions within parametric curves. I don't say parametric or polar curves. Nice example of this, maybe I've got a parametric curve that does that for me. I should be able to calculate the entire area here. So this curve does not satisfy the vertical line test or the horizontal line test, so I can't use regular calculus to calculate that area. I'm going to have to use something else. We can do that using the following formula. So the total area is going to be 1/2 the t min up to t max of x y prime minus y x prime. This is actually going to always calculate the signed sector area, and I'm going to describe what that is in the shape below. Sector meaning away from the origin. You can imagine if I'm traversing this parametric curve from t min up to t max, if I traverse it in a counterclockwise direction, I'm going to compute the area of the sector that spans out from the origin. Now, of course, if my curve happens to be a closed loop, then the sector area is equivalent to the total area. And so you have sectors. If you're only a portion of a loop, the sector is with respect to the origin. It's kind of a little wedge with respect to the origin. But if you have a closed loop, then you can always get the full area. And that's the second statement I make. More importantly, if it forms a closed loop, technically, we have to be mathematicians about this. This closed loop has to encircle the center point exactly once in a counterclockwise fashion. And then you end up that the area of the closed loop is the same integral that you saw before. Now, what is this formula? This formula, in the first case, where you are allowed to compute just maybe a sector if it's not necessarily a closed loop, that's called the Leibniz sector formula. Named after Gottfried Leibniz, one of the fathers of calculus. Sector formula computes sectors of regions. If you do have a closed loop, which is the second case, the formula looks exactly the same. It's just whether or not we're attributing it to a closed parametric loop versus an open parametric loop. The second case is actually a special case of Green's theorem, which is a topic for multivariable calculus if you continue on in your calculus career. So this is a very special case of Green's theorem. We're not going to go ahead with the proof. It's quite a bit of work. It is in the appendix in the book, though, and it's quite nice. It's a very elegant proof, but we just don't have time for it. You can directly calculate the area of a polar region, really a polar sector, directly out of this by the same process we use to convert the arc length formula from parametric to polar. So if we just represent the polar curve in parametric coordinates, x and y, then you just go ahead and grab your formula. Remember what it looked like. It was x times y prime minus y times x prime. And so what have I actually calculated here? I have x, and then here's y prime, and then we have y, and then here is x prime. And if you go ahead and simplify this, what do you know you're going to see? A lot of Pythagorean identities. Well, number one, you get a few terms that cancel because we end up with a r prime cosine sine, as well as a negative r prime cosine sine. So those two terms completely cancel, but you do end up with r squared cosine squared, and you have a negative, so positive r squared sine squared that shows up. So r squared cosine squared plus r squared sine squared, also known as r squared cosine squared plus sine squared. You end up with just a 1/2 r squared for the polar sector area. That's quite a nice little elegant formula. You can really think about it even as the integral theta min to theta max of the integral 0 to r of some other radius r, capital Dr, There we go, and then d theta, right? Because the antiderivative of this capital R would be what? R squared over 2, R squared over 2. So a lot of people like to think about it like that. In this setting, you're really visualizing that this integral is computing, if I'm really computing some sort of sector area, so there's maybe my theta min and theta max. Visually, this second integral is saying, so I'm going to integrate in the radial direction over and over again until I eventually end up at my maximum values. So I'm adding up all of those like one-dimensional lines, starting at a radius of 0 out here and ending at a radius which is defined by the polar curve r of theta. So that's how, two interpretations of the formula give the same answer. And we're just going to go ahead and apply both of these formulas now. So let's look in a parametric setting, the area of a two-dimensional raindrop. So here's a cute little parametric raindrop. We're going to compute the total area inside of here. So how would I compute the total area inside of this lovely shape? Well, to start, unfortunately, we are going to have to do the thing that I don't think many of you like to do, actually find a set of parametric functions which describes this curve or this region. It's a good skill, right? The real world does not present formulas to you, it presents shapes to you. So it is our job as mathematicians to be able to come up with the functions by ourselves. In this setting, we can actually see, if we look closely enough, that this lower loop is a circle, and the endpoints of the circle here and here are going to be, well, it's a circle centered at 0, 0 of radius 1. Here's my center 0, 0. It looks like we've gone exactly 45 degrees up there, so that's got to be the point 1 over root 2. 1 over root 2, that's our pi over 4 unit circle point, as well as our 3 pi over 4 unit circle point, negative 1 over root 2, 1 over root 2. So we'll parameterize that circle, as well as parameterizing this line segment, as well as parameterizing this line segment. So we'll have two line segments, as well as a circle. What do we suppose this top height is up here? It's approximately 1.4. I'm a little more clever than that. This is actually 0 root 2, right? Because I'm telling myself that this is probably also a 45-degree angle. If that's a nice right isosceles triangle, then that'll end up at a y value of root 2. Okay, so these are all of the parametric curves we're going to have to come up with. We're going to determine the area here. How am I going to actually get them? Well, let's give myself the time windows 0, 1, 1 to 2, and 2 to 3 for this parametric curve. And because my formula, I'll say this, my area formula requires that I move once around counterclockwise. And so you can choose to start and end wherever you want. I'm going to choose to start and end up here. And if I'm going counterclockwise, I have to go down in this direction first. So I'll say maybe use the time window 0 to 1 for that little line segment. And then let's go all the way around the circle in the time from 1 to 2. And then I end up here. Let's make sure we're counterclockwise this whole time at the other line segment. And then we're going to finish up going from 2 to 3, this very last line segment. So we'll have to connect all of those dots respectively in a nice counterclockwise fashion. Well, my first line segment connects to the point 0 root 2, that was my very tip top, to the point negative 1 over root 2, 1 over root 2. And I'm just going to use my line segment formula from the parametric curve section of the book for this. If I simplify that formula, I get something a little bit prettier, but a lot of root 2's sitting around, which is too bad. For my circle, my portion of a circle, we're going to have to be clever. Okay, so I'm going to look at this circle. We start there, we end there. How much of an actual rotation is this? Well, we're missing last quarter turn. Well, how much is a quarter turn? That's pi over 2. Pi over 2, well, I'm starting over here at really, you could think about this as what, negative 5 pi over 4, and I'm ending at pi over 4. Okay, so starting at negative 5 pi over 4, ending at pi over 4 over a time window of 1 to 2, how could I make that work out? The easiest way is to start at negative 5 pi over 4, and then we ask ourselves, how far do I have to move to get to where I want to go? How much to add to get to pi over 4? Well, if I add pi over 4 to 5 pi over 4, I get 3 pi over 2. So I'm going to add 3 pi over 2 at the time t is equal to 2. How do I do that when t is equal to 2? I'm just going to subtract 1 from 2 to multiply that 3 pi over 2. So that's going to give me my counterclockwise rotation around the circle. Lots of ways to get to the same result for parametric curves over that time window. That's going to be the one I use here. And then we're going to finish out this very last line segment from 1 over root 2, 1 over root 2 to 0, comma root 2, just by using my line segment formula once again with my time window 2 to 3. Okay, so I've got my 3 sections. This is my first section, my second section, and my third section of my parametric curves. If I combine them all together to piecewise functions, that's what you're looking at. Doesn't look great, but no one ever said grabbing shapes from the real world would. We're going to go ahead and plug this in to our area formula, which is 1/2 t min to t max x y prime minus y x prime. Now, how in the world am I going to calculate derivatives of these objects, or at least integrals of derivatives? I'm going to break my integral up into the 3 time windows. So really this is going to end up being 3 separate integrals over each of the 3 separate time windows, 0 to 1, 1 to 2, and 2 to 3. And when I break my integral up into 3 time windows, I'm just going to compute xy prime minus yx prime of this first time window when I'm dealing with 0 to 1. And so here is x, here is y prime, here is y, here is x prime, and then later I'm going to have to simplify that. I can do the same thing with the next time window. From 1 to 2, I'm using the cosine and sine versions of x and y. Here is x, here is y prime, here is y, and here is x prime. Then I'm going to have to simplify those later. And finally, for the third time window, from 2 to 3, here is x, here is y prime, here is y, and here is x prime. So I'm just grabbing each of them from the piecewise functions separately, and now I'm going to have to simplify all of these. It's not too bad to simplify, right? Because I'm going to end up with, well, I guess a positive 1/2 t there. I'll end up with minus, so plus, I'll end up with root 2 over 2, I'll end up with a plus 1, and then I'll have a minus 1 over root 2 times 1 over root 2 t minus 1/2 t. Turns out, how does it simplify over that region? It simplifies to 1, so that's pretty great. Then if we actually look at our cosines and sines, what do you expect is going to show up? The Pythagorean identity. And so cosines and sines, we're going to actually end up with 3 pi over 2 cosines squared. 3 pi over 2 cosine squared. We're going to have a negative, but with an extra minus sign, so a plus 3 pi over 2 sine squared. Sine squared. Now you've got cosine squared plus sine squared. This is just going to simplify to 3 pi over 2. And in our last setting, we've got 1 over root 2, 1 over root 2. That gives me a 1/2. We've got negative 1 over root 2, 1 over root 2 gives me a minus 1/2 t minus 2. We've got a negative 1 over root 2, negative 1 over root 2 gives me a positive 1/2. And we have a negative 1 over root 2, negative 1 over root 2 gives me a positive 1/2 t minus 2. Turns out my negative 1/2 and positive 1/2 cancel each other. The 1/2s add together here and here, and I just get another copy of 1. So these really do simplify quite nicely if you know, somebody like me is your professor and gives you a good parametric region to calculate the area over. Now we're just going to have 1/2 the integral 0 to 1 of 1 dt. That was the first time window. 1/2 integral 1 to 2, 3/2 dt. Second time window, 1/2 integral 2 to 3, 1 dt. Third time window, compute the antiderivative on the bounds of each of those. You get 1/2 plus 3 pi over 4 plus 1/2, also known as 1 plus 3 pi over 4. And so you know that the total area of this region, using parametric curves in our formula, is 1 plus 3 pi over 4. Definitely not something you would have been able to do with regular calculus techniques when this violates both the horizontal and vertical line test. However, the clever ones of you maybe have noticed that you could just dissect this shape into a 1x1 diamond or a square and a 3/4 circle of radius 1. What do I mean by that? I mean it looks like this. What's the area of a 1x1 square? The square is equal to 1. What's the area of 3/4 of a circle of radius 1? The area of the circle, and really it's a 3/4 circle, is going to be 3/4 pi r squared, pi times 1 squared. What happens if I add 1 to 3/4 pi? Yeah, I'm going to end up with 1 plus 3/4 pi. So yes, this was technically a problem that we went through a whole bunch of extra work to just get a weird collection of integrals for. That did eventually simplify to 1 plus 3 pi over 4, but you could imagine maybe somebody's not asking for such a geometrically well-behaved shape in the future. The area formula for a parametric curve will still work. I mean, ellipses, it'll work for. You can make dumbbells using some sines and cosines. All of those hypocycloids we talked about, the regular cycloid we talked about, all of these you can calculate the area for that your regular calculus knowledge just wouldn't apply, or even geometry knowledge wouldn't apply for. Let's finish off with one area of a polar region. We're going to work with the Archimedean spiral, shown below, and recall the polar form of the Archimedean spiral is r of theta is equal to theta. How could I calculate this particular region's area? Well, you might think right away that I just need to find the bounds of theta that start and end this region. So this, for example, starts at theta is 2 pi, because that's after I've made one full rotation. And I end out here at theta is 3 pi, because that's one extra half rotation. But it's not quite that easy, because how does areas work? It's just if I start here, the area is going to sweep out the sector area, and like everything's hunky-dory until you get to the second half, and your sector starts to cover up that first area that in the bottom right down here, you don't want this area. And so how are we actually going to calculate the area we're looking for? We're going to calculate the sector area that I just kind of highlighted, which is the case from 2 pi to 3 pi. But we're going to go ahead and subtract the miniature area, which is the case where we start at 0 here and we're going to end at pi. And so our total area is going to be the big area, which is from 2 pi to 3 pi, minus the small area, which is the one from 0 to pi. So we're just going to go ahead and compute those areas out using our formula. Let's recall the formula. It's given right here, r of theta squared d theta. And we're just going to plug in our Archimedean spiral formula, which was that r of theta is equal to theta. And now by plugging in theta for r of theta in both cases, we calculate the outside area and we subtract the inside area just using the power rule. It's theta squared, which is going to go to theta cubed over 3 in both cases. We just evaluate everything out. We end up with 3 pi cubed. So it turns out that the area of this original region I cared about is 3 pi cubed. Nice little thing to know. But you can see, all things considered, why we studied all those integration techniques, why we studied polar and parametric curves. It is really a wide breadth of arc lengths and areas we can calculate now with all of our knowledge. Anyway, we've only got one more video after this. I hope you're looking forward to it. We're going to talk about volumes of objects and surface areas of objects in 3 dimensions that we can obtain by rotation. I'll see you then. Bye.